In this demonstration, we're going to be covering STEM imaging, and specifically atomic resolution STEM imaging. So when you're doing any kind of STEM imaging, and particularly when you're trying to do high resolution STEM imaging, which is atomic resolution STEM imaging, you need a clean specimen. So you should always, if permissible, plasma clean the specimen before starting your session. So the specimen we have in here is a silicon lamella prepared via FID, and we plasma cleaned it in our Vishoni Instruments 1020 plasma cleaner for 2 minutes before loading it into the column. The other thing you need to keep in mind too, if you're working with a large single crystal, which we will be today, a lot of the same issues with getting a good high-res image are also relevant in getting a good high-resolution STEM image. So when you hear just high-resolution image, that usually, without any qualification, implies conventional or static beam imaging. And so you have to delineate that from high-resolution STEM imaging. But the same considerations apply in many cases, specifically the issue of zone axis alignment. So you can see we have the double tilt holder loaded here, and we're going to need that again for zone axis alignment. And in fact, it's probably even a little more critical when doing atomic resolution STEM compared to just conventional high resolution imaging, that you have really precise zone axis alignment. Okay, so we have the specimen loaded and the column valves opened up, and so really there are two, actually really only one technically absolutely critical thing before heading into STEM mode. So if you're going to go into STEM mode, full alignment of the instrument in conventional mode isn't necessary, because STEM mode has its own specific alignment, with the notable exception being that you have to make sure that the specimen is at eucentric height before entering STEM mode. So again, remember how that's done, right? You come over here, eucentric focus, make sure you're in SA mode, which we are, okay, and then adjust Z up or down to minimize contrast. I was already at eucentric height, so again you can see right about there, and then I go too far, it's right about there. Okay, so we're at eucentric height. The other thing that it's a good idea to do is to get the zone axis alignment close in conventional mode before going into STEM mode. Once we are in STEM mode, we will have to do another more precise zone axis alignment. So just because your zone axis alignment looks good in high-res mode doesn't mean it's going to be necessarily good enough in, or I should say in conventional mode, it will be good enough in STEM mode. So again, as you can see in the sample here, I'll increase the magnification so we can see this a little better. Okay, so you can see here in my specimen, I've got kind of 3 layers there. So that leftmost layer is the silicon substrate, and that layer on the right is actually FIB deposited platinum, and then that layer on the surface, that layer between the two, that light layer, is actually surface damage from the direct deposition of the FID platinum onto the substrate without any sacrificial protective layer. So what we're interested in here, usually when you're looking at samples like this, you're interested in looking right at the surface. So you're trying to get good zone axis alignment, in the case of our substrate, right where the substrate ends at the surface. Okay, so I can maybe move over a little bit here, okay, and then I can go into diffraction mode with the diffraction button, okay. And so you can see I'm actually fairly close in my zone axis alignment. You don't have to be extremely precise here because again, we're going to get into STEM mode and we're going to have to do another zone axis alignment. Let me increase the camera length here just so that's maybe a little easier to see. Okay, so this is a 110 zone axis. You can see we are reasonably close. Again, if we weren't close, we'd see something like this. Move the sample back. As you can see, I have a Lowy circle that's open, meaning I'm no longer on the zone axis. So again, you want to close that circle. Okay. Now keep in mind again, you have to get good zone axis alignment, just like when you're doing high res, has to be at your area of interest. So your area of interest, again, is your area of interest, but remember the sample's probably not flat, so even though the alignment looks good here, we go back into image mode here. We have to ask, where we're looking at here. So clearly we're not looking right at the surface anymore. Okay, so if we go find the surface again, where are we? Yeah, there's the surface. Okay, so if we're closer to the surface now, we go back into diffraction. So you can see we're not quite still there. I'm going to make another adjustment here with my alpha tilt just to get it a little bit closer. Okay, again, if I'm seeing the, yeah, so that looks, that looks a little bit better. Again, we'll have to do a fine tuning of this once we go into STEM mode. So I'll go back into image mode. Okay, and again, since I messed with the tilts, I'm just going to quickly reestablish eucentric, hit eucentric focus, adjust Z until my contrast is minimized. I've actually not that far, but a little bit of an adjustment. Okay, so at this point, we're ready to exit conventional mode and head into STEM mode. Before we do that though, one thing to keep in mind is when you're doing STEM alignment, you need a region of the specimen that is mostly amorphous or has amorphous regions in it. So fib platinum works great for doing that, or if you have a layer that's completely amorphous, that works great for doing that too. So you can see that dark layer on the right, that's actually fib platinum. So if I center that in my image here, when I go into STEM mode, I'm gonna be starting basically over that, okay? So I'll already be over an area that works good for doing alignment. If you start over an area that's crystalline, you really can't do STEM alignment effectively that way, and then you have to search around for an appropriate region to do that with. But if you already start on an appropriate region, then you've already set yourself up to do the alignment easier. And so with that, we will discuss getting into STEM mode. Okay, so to go into STEM mode, find the STEM tab, hit the STEM button. Really easy to do. Unfortunately, this is not the only thing that's necessary. We do have to now align the instrument in STEM mode if we want to get the best possible image. When you enter STEM mode, you need to reset the spot size. So the spot size setting that was used in conventional mode doesn't transfer over into STEM mode. So if I come to the beam tab here, you can see I'm at spot size 2, my numerical value. So again, as was discussed in the general operation video, the lower I go in numerical value of spot size, the bigger my probe size is going to be. So if I want to do high resolution imaging, I need to use a probe size that's way down here. And usually what we do on this instrument is we use spot size 10. You could use probably 8 or 9 as well and get atomic resolution imaging, or 11. 10's kind of a nice compromise though between 10 and 11, because you are going to get more current at 10 than you will at 11, but you should get a smaller probe at 10 than 9. So that's one thing to keep in mind. Now if you're doing analytical work like EDS or EELS, you're going to operate in this end of your numerical spot size. So right now we have this set up for a more appropriate analytical setting. So what I'm going to do though, just for demonstration purposes, because it's much easier to demonstrate the alignment with a low numerical value of spot size because the probe current is higher, I'm going to leave it at 2 just for demonstrating the alignment, but I'm going to, when we pull up the actual image, before I do that, I'm going to reset the spot size to 10 and perform the alignment and then show you that image in TIA, because that's what we would need if we wanted to do atomic resolution imaging. So the numerical value of spot size has been set, so we can discuss doing the alignment now. So I'm in the STEM tab. I'm going to come down here to my STEM detector control panel. You want the camera length set fairly high for doing this because it's going to make it easier to see the ronchigram on the viewing screen, which we'll discuss in a minute. Normally when I'm doing this, I use the focusing screen in the binoculars. We obviously can't do that with the camera here. So I'm going to use 490 for demonstrating this with the camera, but normally I would use 200, just viewing it on the screen with the focusing or with the binoculars, but we'll leave it at 490. So again, the camera length is the magnification of the seabed pattern. We do have a seabed pattern because we do have a converged beam that is being projected onto your STEM detector. And we will talk about also the effect of the camera length on the image once we get done with alignment and we have an actual image. Okay, so here on the viewing screen, you can see I have basically a seabed pattern that's just a direct disc because we're over the fib platinum, which is finely grained and partially amorphous. And so the direct disc of a seabed pattern is also known as a ronchigram, and that's what we're going to use for doing the STEM alignment. So right now I've got my number 2 C2 aperture in. I'm going to increase this to 4 for alignment purposes because it's going to allow me to see more of the ronchigram. So now the first thing I have to do is I've got to roughly center my C2 aperture. So over here, I have my focus knob, I have my focus step set to 5. And I'm just going to pulse the focus here. Okay, so I can actually see where the ronchigram is expanding and contracting. So it's actually, if you watch my hand, it's actually on this closer to us. So I'm going to shift the aperture down. Okay, and then I'm going to pulse it again here. Alright, so right about there. Okay, and you can move the stage a little bit. But right about there, I've got what I want. Okay, and actually I'm going to increase the camera length just a little bit more. Okay, so now in my ronchigram there, let's see if I can get a better focus here. Okay, in my ronchigram there, you can see a lot of features. You can see rings, you can see how the ronchigram is expanding and contracting when I adjust the focus. Okay, and so you need to get to this point to effectively do the STEM alignment. So this is really almost kind of half the battle, is you have to find the ronchigram and be able to see those rings and the expansion and contraction of the ronchigram. So the first alignment that I need to do here, come to the Tune tab, click Rotation Center Intensity. Okay, now if you look here on the screen, see if I can get a better focus here. You can see a little pulsing in the ronchogram. If you come to the focus knob here, you turn this counterclockwise, that turns off the pulsing so you can pulse manually. Okay, so now I'm using the focus knob and I'm pulsing manually. Okay, so what you're looking for here now, and this is difficult to describe, okay, it's kind of abstract, but what you're looking for here is how is the ronchogram expanding and contracting. Okay, as it expands and contracts, you should see it do so in a way that's best described as concentric. Okay, so basically like it's expanding and contracting into and out of the plane of the screen, not up and down, left and right, or at an angle. So if we look here right now, it's probably a little hard to see, but the ronchogram is actually expanding a little bit over to the right, and actually what I can do here is I can exaggerate this so it's a little easier to see. Okay, so I'm using the focus knob here, or not, sorry, the multifunction knob. Alright, and now that's actually a little bit worse. You can see it's expanding a little bit off to the right. It's also expanding down. Okay, so what you have to do now is your multifunction knobs are activated to adjust the beam tilt. Okay, so normally when I do this, I bottom this out so it's at the finest setting. Okay, because usually higher than that is just too coarse. Okay, and so now again it's a matter of I'm pulsing the focus, I'm seeing how my ronchogram is expanding. Okay, so your X multifunction knob adjusts left right movement, your Y adjusts up down. Okay, and I don't have it in front of me, but there's a little cheat sheet that kind of tells me how to turn the knobs based on how it's tilting. So right now I'm turning clockwise, so I'm going to turn it, and then I'm going to check the... Alright, so it looks like maybe it's getting a little bit better. Keep going clockwise here. Alright, so it looks like it's maybe coming down a little bit. So that's worse. I'm adjusting the Y now. Alright, so that actually looks pretty good. One thing you should keep in mind here is that the position of the ronchogram within the C2 aperture may change while you're doing this. So that's not necessarily problematic as long as you can still see the ronchogram. I can, of course, just reposition this. Okay, so now if I look again, I'm basically getting expansion, contraction, straight into and out of the page. Now, if I was doing this to be the most accurate possible, I could, I would do this with, again, the binoculars and the focusing screen and a shorter camera length. Okay, but again, for demonstrating purposes, that's a little hard to do. So we have it just here on the screen. And so that's the rotation center. Alright, so rotation center is done. Select done. Come down here to the Stigmator tab and select Condenser. Okay. So again, you've got your ronchogram here. Okay, and I can see those rings in the ronchogram. Those rings, as viewed on the screen, should be circular if I don't have any condenser astigmatism. Okay, so if I have I'll throw this off here so you can see. Okay, so now I actually have, I don't have rings anymore. I've got these like orthogonal, they almost look like streaks. They reorient by 90 degrees. Okay, that's bad news. That means you've got some bad condenser astigmatism present. I do want to stress that it is the condenser astigmatism that needs to be corrected, not objective or diffraction when you're doing this, or you're going to end up lost. Okay, so right about there. That looks pretty good. And now when we're in, and now I'm throwing it off, now it looks worse. Yeah, so now I have the streaks that reorient. I do have a live video of this from another TEM done on a digital camera that is a little bit easier to see, that I will also post at some point. Okay, so even though we have it corrected fairly well here, we're going to have to do another correction with the actual STEM image as well. So this isn't it by any means, but we have it in the ballpark, if you will. Okay, so again, come over to the Stigmator panel and select none. So then the last alignment step is C2 aperture centering. So it's very easy to see here again. I'm pulsing the focus knob. I can see where I'm expanding, contracting. So now you need to center your C2 aperture around that point of expansion and contraction. So for doing high resolution imaging on this particular instrument, we use the C1 aperture, which is the smallest, or sorry, the number 1 C2 aperture, which is the smallest. That gives us an optimal semi-angle of convergence. So if you go up from there, you end up with a bigger probe because of aberration or spherical aberration induced broadening. You will end up with more current. So if you're doing analytical work, that may be something that's tolerable, but since we're talking about imaging, we're going to put in aperture 1. And so you can see I'm not really centered. I'm going to go ahead and move this. Okay, and now again I've got I'm still not centered. Alright, and I need to come down a little bit more. Again, I would normally do this on the viewing screen with the binoculars. Alright, so that looks pretty good right there. Okay, and so this is the basic alignment in STEM mode. And so now, when we get to the actual STEM image, there are some additional tweaks we can do, mostly with the condenser astigmatism side of things. Okay, so as I said earlier, I have the spot size set lower here just for demonstration purposes. But what I'm going to do is, for demonstrating high resolution, I'm going to change this to 10. Okay, I'm going to change it to 10, and I'm going to go through the alignment again. Alright, so instrument's been realigned at spot size 10, and so now we can actually start getting a STEM image. So I come back into the STEM panel, I hit search. That's going to automatically insert my detector, and now here's where you can set the camera length to get the type of STEM image you want. If you want a HAADF-STEM image, you need a short camera length. So there isn't any universal consensus on what detector collection angle constitutes HAADF, but a general guideline would be maybe 50 milliradians as an inner collection angle for your ADF detector. So I'm actually going to decrease this to 100 because I know that actually does give me an inner collection angle of the detector that's a little bit more than 50. So now if you look on the screen, okay, it's really faint, and that's, again, we're at spot size 10. You can see now the seabed pattern. Okay, so beam is scanning. So as I'm scanning, I'm seeing the seabed pattern, right, which is coincident with where the probe is located. So now one last alignment I can do here, okay, and this is tough to see without looking at the binoculars, okay, but I can actually see, is my direct disc centered inside of the ADF detector rim? So if I look through the binoculars, I can actually see the detector rim, okay, and then I can actually shift the seabed pattern to center it if it needs to be centered. So that would be done. I'm here to tune, diffraction alignment. Now my multifunction knobs, okay, will shift the seabed pattern, okay? And so I'm going to do this here really quickly. I'm going to take a quick look and see, and if they are, I'll make an adjustment here. Okay, so my seabed pattern didn't really need to be shifted at all, so I didn't make any adjustment with the diffraction alignment. So I'm going to go ahead and select done. Okay, come back to the STEM tab. So now you'll notice here I'm not really seeing an image. Okay, the reason for that is my detector settings are contrast, brightness need to be adjusted. So this can be done automatically, and this will usually give you a fairly satisfactory result. Just click on Auto CB, and you can see now we can see the image pretty clearly. There's a way to manually adjust contrast brightness, which we can go over here in a little bit. So a few things we can do here. We again, if we want to do atomic res imaging, we need to make sure we have good zone axis alignment. Okay, so to do that, you need to look at the seabed pattern. So again, right here, right, this light region, this is our platinum, this is the surface damage from the gallium ions, and then this is your undamaged silicon. So we want to see, again, if we're interested right here, we want to see what the seabed pattern looks like right here. Okay, so in order to do that, I've got to stop the scanning. So if I select search, that freezes the beam. So now the beam is sitting here. If I want to control the beam position, come down here. This is the beam position marker. Click in the image, and now I can drag the beam wherever I want. Okay, and now it's going to be tough to see here, but now the seabed pattern is changing based on where I put this. Okay, so if I drag it all the way off here, I don't see anything except for a direct disc. Okay, so now here's where you have to look at the seabed pattern and see if you're well aligned right here. Okay, if you're not, you have to make an adjustment with the tilt, and just like adjusting the tilt to get zone axis alignment in conventional mode, if I do that, I'm going to end up being away from eucentric height, and then I end up having to reestablish eucentric height. So that is trickier to do in STEM because there isn't a eucentric focus button in STEM. Okay, so it doesn't work the same way in STEM. What you have to do instead is we have to start with a focused image. So I'm going to come back over here. We know the sample's at eucentric height because we specified it, okay? And I'm in search mode here. So in STEM mode, magnification works essentially the same way. Okay, you can see here, I'm changing my STEM mag. Okay, I'm going to drop my step down here. Okay, so you can see the grains in the platinum. These make good features to focus on. Dropping my focus step down to 3, and I can get a good a focus as I want. Okay, so that looks pretty good right there. So now I'm in focus and I'm at eucentric height. Okay, so now I can make an adjustment to the tilt. Okay, and my image will likely go out of focus. if it goes out of focus, I need to readjust the height to get it back in focus. Okay? So in other words, I can turn off search and freeze. I can look at the seabed pattern here, see if it's off axis or not. If it is, I can make a tilt adjustment, and then I need to bring the sample back up to eucentric height, okay, with the Z control. So I'll make a tilt adjustment. It's going to be hard to see the seabed pattern because of how faint it is, because we're at low current, but I'll make a tilt adjustment just so you can see how the image goes out of focus, and then we need to bring it back up by adjusting the Z control to stage. Alright, so I made an adjustment with a tilt, and you can clearly see the image is blurry. So now I'm adjusting Z here to get the image focused again. Again, you don't want to adjust the focus knob when you're doing this. Alright, so there we go. Again, you want to get it as good as you can get it. Obviously, there's only so good you can get it just by adjusting Z, but that looks pretty good right there. Okay, so I know from looking at the seabed pattern that in here I've got an area where I've got good zone axis alignment, and so that will give me a good high resolution image. But before we do that, I'm going to go ahead and just delete the marker there. Oops, yep, just hit the delete button. Okay, if I hit search again, so I got a live image here. Some of the other things we can do with the STEM image. So we did a rough, not to say rough, but we did a basic adjustment of the condenser astigmatism earlier. Okay, one way you can adjust this more finely, and actually you will need to do this when we do the atomic res, okay, is to look at the actual image. So now I'm looking at the fib platinum here, and I'm looking to see, I'm changing the focus right now, okay, I'm looking to see as I change the focus if I'm seeing any sort of streaking in the image as I go from over to under focus. I don't really see any, okay, so my astigmatism correction is probably pretty good. That's not to say that when we look at an atomic level, which we're not at yet, that we may need another adjustment. Okay, so but anyways, if this was off, right, I'm activating the condenser stigmators here. Okay, so what you're going to see here, if this is off, right, so now if I go through focus here, okay, my images, I see streaking of those of the grains, okay, and I deliberately threw that off. Okay, so all you want to do here, use your multifunction knobs, use them one at a time, get the image as sharp as you can get it with one, okay, and I only adjusted Y, so I'm not going to do it with the X here, but you get it as sharp as you can with one, and then you go back and forth through focus here, you look for any more streaking, which we don't see. Okay, so we've got the astigmatism pretty well corrected. Again, at an atomic level, we'll have to make another adjustment though. But this is clearly good enough for this level of detail. We can clearly see the grains of platinum. So once you have a good image focus here, there's another mode here you can use, which is called preview. Okay, so this is intended to kind of show you how the final image is going to look. So as you go from search to preview to acquire, the number of pixels in your image increases. So this has more pixels than search mode, but less than acquire. But this is more representative of what your final image is going to look like. So some of the things we can do here, you'll notice I have this interface. Okay, if I want this interface vertical, I can adjust that in the STEM image. Okay, so if I come back here, I have this rotation parameter. If I click on that, okay, a negative rotation is a clockwise rotation. Okay, so if I go, I'm going clockwise here, or counterclockwise I should say, my rotation is getting positive. Okay, you can see that I'm leveling that out. This is usually easier to do if you kind of mag out a little bit so you can see a longer range of the interface. Okay, but you can clearly see how that's now leveling off. Okay, and I've got now a nice vertical interface. Okay, so that's one adjustment you can do. And usually you should do, I know atomically speaking that this is closely aligned, so that's something that you usually want to do. Another adjustment we can do now is we can manually tweak the contrast brightness. So if I come back up here to STEM imaging and I click on scope, okay, that pulls up here the grayscale value along the line scan as the scan moves down. Okay, so if I come back to STEM detector here, click multifunction knobs, my multifunction knobs are now addressing or adjusting contrast brightness. Okay, so brightness is going to shift all of these grayscale values down. So I want this basically as low as I can get it without bottoming all the way out like that. So something about like there. And now I can use the contrast, okay, to increase that. I may need to adjust brightness a little bit accordingly. But now I'm basically using the whole dynamic range of the detector. Okay, so this is what you want to get the best, the image with the best contrast in it. Okay, so once you have this, you can turn off scope. Our focus is good. And then we can hit acquire to acquire a final image. While you're doing that, an acquire will usually take 30 to 60 seconds. You don't want to do any talking or any sort of jarring motion because again, this is a serial process and it does take a while. So I'm going to hit acquire. We'll watch it acquire for the first few seconds, and then I'll cut the video and then we will resume afterwards. Okay, so that's our final acquired STEM image. You will notice these black lines. Those go away. Just click on the image and they're removed. But that's a nice looking HAADF-STEM image. Clearly though, it's not atomic resolution. So if we want an atomic resolution image, again, we've got to find the area that's zone axis aligned. Ideally, that, and we need to bring that to the center here. So I'm going to go ahead, I'm going to go back into search mode. Okay, let me take a look here again. All right, and so this area looks reasonably well aligned. Again, the better alignment you have with this, you know, the more accurate the result. Move up here a little, see if that looks worse. Again, because the samples are bent and not straight, it's very, very common that you're only going to get good zone axis alignment over really a pretty limited specimen position. Come on. Alright, so I'm just going to pause here, check my CBAD pattern, see if I can't find my good alignment spot, and then we'll resume. Alright, so I have my area that I know has good alignment, fairly centered here. The focusing adjustments we're going to be making are really fine, so you want to make sure that your sample's already in reasonably good focus before you do anything. So again, I'm looking at the grains in the platinum because those are an easy thing to check out to see if the focus is good. Yeah, and that looks fine. Alright, so I'm going to increase my magnification here. So really, to see lattice detail or atomic res detail, you've got to be over 1,000,000 X indicated. Usually, you know, in this range is kind of ideal, the 5 to 7 range. Okay, and so now I'm going to put my focus step down to 1, and I'm just going to slowly change my focus here, and I should be able to start seeing, okay, there it is, it's coming in, right there. Okay, so I can start to see some atomic resolution detail. Once I switch here to preview mode, it'll be more apparent. Yeah, and there it is. You can see, again, every time I talk, that's bad, right? That's a vibration. Okay, so the question now is doing the astigmatism adjustment again. So you need to make another adjustment when you're talking about atomic resolution imaging. So again, I'm going to come down here to Condenser. Okay, put your adjustment at the finest setting. And so now it's really a matter of, one at a time. I'm just going to adjust my multifunction knobs until I can get the sharpest image. Okay, that's actually not too bad right there. One thing you need to keep in mind too is that we may be building up contamination. I can actually see the contrast getting worse with time. If I back out the magnification here, yeah, you can see if you see this light area, we're building up contamination there. So this is something that you potentially deal with when you're doing atomic res STEM, even though you plasma clean the sample. So you kind of have to be quick sometimes. I'm going to move down here really quickly. Zoom back in. And again, I can turn my scope on. And I'll do an acquire and be quiet. Okay, so there's my final acquired atomic res STEM image. Not the best one, mainly because of the sample. So even though we have good zone axis alignment, it is an old sample and it is a little bit dirty, and that is going to impact your STEM image. So fresh samples are always best when you're doing this. Okay, I can mag out here just a little bit. Okay, so if I go right here, even at this mag, this is kind of the lower end 1.8 million X, we can see atomic level detail. And so there's our atomic resolution STEM image, again kind of the lower end in terms of magnification, where we can see atomic level detail. So when you're done in STEM mode, which we're gonna finish up here, things you want to do, you want to make sure beam isn't blanked and we're not searching or preview. So basically we just have a static beam. If we adjust the rotation here, you want to zero that out and then just hit the STEM button. Okay, so the STEM detector retracts automatically. And now something to keep in mind is that your C2 aperture alignment in STEM mode will not be the same as it is in TEM mode. I need to go back to C2 aperture 2 here. Okay, and now I need to realign this. Okay, so you can see clearly that needs to be adjusted. Okay, get it back in the ballpark so it's not off kilter for the next person. Okay, and with that, that concludes the demonstration on STEM imaging.